Kellyanne has $20,000 to invest. She puts half, that would be $10,000, of the money into an account that grows an annual interest rate of 0.9% compounded monthly. At the same time, she puts the other half, the other $10,000, into an account that grows continuously at an annual rate of 0.8%. Which function represents the value of Kellyanne's investments after T years? So, speaking of knowing your formulas, if you don't know your formulas for compound interest and continuously compounded interest, you do not have a prayer. And this is honestly the first time I've seen them combine both of them, so this almost even ups the ante a little bit. So the first 10,000 is going to look like this. So your formula is final amount equals initial amount, 1 plus your rate divided by n. That's the number of times compounded, times, or to the nt power. So your first half has an initial amount of 10,000. 1 plus, now 0.9% is 0.009. Compounded monthly means an n of 12. To the 12, and we don't know how long we're waiting. It says how long will these be worth after t years, so 12t. That's the first 10,000. The second 10,000 comes from the PERT formula. So P kind of does what A does. It's your initial amount, so that's $10,000. And then E, we know, is just a weird number. The rate is 0.8%, so 0.008 T. And so your total is going to be adding this half of the investment and how it grows to this half of the investment. Now, just from the 10,000 E to the 0.008 T, I like that and I like that. This one didn't change the percentage to a decimal properly. And then if I look at the front side of this, the difference between these two is that this one is growing at 0.9% every 1 year, because this is technically T over 1. And this one is growing at 0.075% at a frequency of 12 times per year, which would in fact be, 12 times per year would be monthly. So if you actually, well, you see the 12t, but if you actually crunch that, 1 plus 0.009 divided by 12, that's the 1.00075 to the 12t power, so 4 is what we're looking at. If you don't know those formulas, you have no prayer. And even knowing them, it's a somewhat tougher question just because it's combining multiple types of growth. Okay, and this one, which graph represents a polynomial function, they're all polynomials, that contains this as a factor. Now, if this is a factor, we should be able to see if we can find, tee it up and find roots. So if I were to set this factor equal to 0 and keep factoring it, I believe it factors into x plus 1 and x plus 1, which means we have a root at -1, and it's a double root. So if it's a double root at -1, double because it's happening twice, it should bounce at -1, and this one bounces at -1. This one does not. That's a single root at -1. That's a single root at -1, and that's a single root at -1. So these are all just going through -1 cleanly. This one's bouncing off of -1. So that's your answer. In 20, we've got sodium iodide 131 used to treat certain medical conditions. So has a half-life. So this is exponential change again. I'm immediately thinking of this formula. Okay, basic exponential growth or change. Not money, so not compounded like we did over on the other page, not continuously. The data table below shows the amount of sodium iodide rounded to the nearest thousandth as the dose fades over time. So from what I have up here, before I jump into the pile, just to fully, if it has a half-life, then it's 1 minus 50%, 1 minus 0.5, and its half-life is every 1.8 hours, so T over 1.8 hours. So they're looking for the approximate amount of sodium iodide that will remain in the body after 18 hours. So I think this is a little bit tricky because if you look from 1 half-life to 2 half-lives, it's half the quantity. From your second half-life to your third, so it becomes a half every half-life that goes by, we have half the quantity. The actual amount of time between there, though, is 1.8 hours. And then another 1.8 hours will bring us to our third half-life, and another 1.8 hours will bring us there, and another 1.8 hours will bring us there. So we could keep kind of tracking this and seeing when we accumulate our 18 hours. But if we want to use the formula, which I think would be smart here, the only thing we really have to think about is what was our starting value. So after 1 half-life, it was 139. So what was it before? So what would it have been prior that when you took half of it, it became 139? So we would just do 139, multiply it by 2, and this actually started out with 278 grams, or whatever the unit is, of this sodium. So if you think that backwards, you have started at 278, half of you was 139, then half of you, then half, then half, then half. So now that we know that the starting value is 278, we can go right up here and use that as our initial amount. 278, 1 minus 0.5, and we're waiting 18 hours, so we'll do 18 over 1.8. And just type that in, and you should be good. Your exponent needs to be a fraction. On my calculator, that's how I have to type that in. So my fraction exponent is in parentheses, and I get 0.271, which is number 3. In 21, which expressions are equivalent to this? Okay, and this is just saying as long as x doesn't equal 0. And the only reason they add that stipulation is because if x equals 0, this whole thing is undefined, so it really can't equal anything. So as long as x doesn't equal 0, what will this simplify to and equal? So I think without looking at our options, if you were asked to simplify this, hopefully you would factor out an x from up top, and you would cancel these x's, and so it simplifies to x minus 4 over 2. That's one way of looking at it. If a binomial is being divided by 2, you could also divide each piece, so that would be x over 2 minus 4 over 2, which would be x over 2 minus 2, which is this one. And this one is just sort of actually a funny thing. I guess, why do they have it in that form? I don't see how this is that, but this actually needs to be simplified. So it already has a common denominator of 2. X minus 1 minus 3 would make x minus 4, which actually is a match. They just kind of separated it in a funny way. So I would say all 3 of them seem to work. 1, 2, and 3. Okay, here we have a quadratic function. They give us the formula for f of x, and they give us the picture of p of x. So this equation is not this graph. So we have the equation of one and the graph of another. The difference between the values of the maximum of p and the minimum of f. So maximum of p and the difference between the minimum of f. So the maximum of p is, right there, 5. A maximum value and the minimum value is talking about the y, the highest y or the lowest y that gets reached. So p has a maximum of 5 minus, and F has a minimum, you might as well just pull your calculator out and look at it. So 4x squared plus 6x minus 3. If you just do zoom 6 and see if we like the look of the parabola, okay, we see our minimum value is somewhere down here. It looks like negative 1, 2, 3, 4, 5, and a little bit more. It's definitely not a whole number. So if you go to your table, and right now my table's counting by 1,000, so that's even worse. You got to set up your table properly. We'll have it, most of yours would probably count by ones. And if I looked at my table, now that I've got it counting by ones, the minimum value that it looks like it reaches is negative 5. But we saw on the graph, it actually is getting lower than negative 5. It's definitely lower than negative 5 right there. The reason that's not coming up on my table is because it's not happening at a whole number x value. Your table is only so good to show you the whole number x values. And so it's probably, somewhere around an x value of negative 1 and a y value of negative 5 would be somewhere near the minimum, but that's not actually it. So you have to know how to use second trace, which is something I'm not really a table person to begin with. This second trace always gives you the exact, and I want the minimum. So select that, and it's going to tell me to bring my cursor to the left of the minimum, then to the right of the minimum, and then it will tell me exactly what it is. So here I go over to the left bound. Once I get to the left of it, hit enter. Then it's going to say right bound. Go to the right of it, hit enter. And then it's going to give me the minimum value between those two sections. And the minimum value is negative 5.25. So maximum and then minus the minimum is a negative 5.25. And of course they've got that double negative there, so 5 plus 5.25 would put you answering this at 10.25. So this is like features of graphs, and we did this way back at the beginning of the year with talking about what's the maximum value, what's the minimum value, where are you increasing. So we're increasing from negative infinity to 2. We're decreasing from 2 to infinity. Where is the graph negative? That means underneath the x-axis. Negative would be from negative infinity to whatever that root number is, negative 1 and change. And then it's positive from negative 1 and change to 5 and change. And then it's negative again from a little over 5 to infinity. So when's it increasing versus decreasing versus constant? Interval notation. When's it positive versus when is it negative? Interval notation. Relative maximums versus absolute maximums. So something like this is a relative maximum, but it's not an absolute maximum because the graph does get higher elsewhere. But at least in this general vicinity, it reaches a peak, and so it's considered a relative maximum. So that was probably something we did in September that it doesn't come up a whole lot, but is fairly simple. 23. Scores on a math college entry exam are normally distributed with a mean of 68 and a standard deviation of 7.2. This immediately has me thinking norm CDF. Normally distributed. If they ask about a probability, I'm going to say it's definitely. Students scoring higher than one standard deviation above the mean will not be enrolled in the math program. So if the mean is 68 and the standard deviation is 7.2, 68 plus 7.2 puts us one standard deviation of the mean at 75.2. So there's really the cutoff. Any kid that is scoring higher than this is not going to get tutoring. Anybody lower is. So how many of the 750 students can be expected to be enrolled in tutoring? So the norm CDF gives us the percentage. So we're going to do a norm CDF, so second VAERS, norm CDF. Your minimum, you want to find your percentage that's underneath. So your minimum is negative infinity, so let's do negative 999. Where's my comma? I don't love this calculator. Your maximum is 75.2, comma. I lost my comma again. Oh. Your mean is 68, and your standard deviation is 7.2. And then that'll give you your percentage. So 84% of the kids are down here, and then that obviously means the remaining 16% are up here. So how many of the 750? 84% of the 750. 84% of 750 will get tutoring, and 84% of 750 is approximately 630 kids. So 631. I'm not sure why that was off by 1. Maybe because right at 75.2 they technically will be getting tutoring. It's just the ones above, so it says higher than one above. But there's not two close numbers, so that makes sense. All right, and number 24, if we're looking to solve this and just actually come up with what the solutions are, it's kind of a rational graph and an absolute value graph. A rational function and an absolute value function, rational equation and absolute value equation. We've never solved by hand, anyway, this type of an equation, and I'm not even sure I could probably play around with it, but it's above where we are for Algebra 2 to have to do this by hand. So given that this is multiple choice, number 1, and given number 2 that they're just looking for how many solutions, treat it as a system. Plug in this function, plug in this function, and figure out how many times they cross. So, that sounds easy, but sometimes they give you a window, and the standard window is no good. So for absolute value, hit math, 3x minus 2, and then a plus 5. So if I do zoom 6, which is the standard window that most of you will see, you can see your crazy rational graph. It was like in 3 parts. It was this part, and oh, now I'm losing it, this part. And then your absolute value graph is that V shape. So there's a lot of action happening right in here. So all of this space looks pretty wasted. So I'm just going to zoom in. Well, I'll change my window. I only really want to see from here to here and get a closer look. So I'm going to go like -4 to 4 on my x-axis and see what we think about this view. There's my rational. And here comes my absolute value. Okay, so how many solutions? So there's definitely 1, there's 2, there's 3, and it's going to cross one more time, it looks like, right down there, 4. 1, 2, 3, 4 solutions, and you're done. We actually aren't seeing the 4th solution. It's somewhat off our screen, but even if we only saw that, you can kind of see that the absolute value is going to run into that curve. If you wanted to, you could open up your Y window from -10 to 10 to -20 to 20. It would just give you a little bit of a clearer look at the 4. 1, 2, 3, 4 times of crossing. So that's the end of our multiple choice. We'll run to our open responses. Justifying why this radical notation is equivalent to this exponential equation using the properties of rational exponents. So we should know that the cubed root is the same as raising it to the 1/3 power, and the 4th root is the same as raising it to the 1/4 power. Then when you have power to power, and this is a monomial, but it's got 2 parts, both of these parts of the monomial have to be raised. So x squared to the 1/3, power to power means multiply, so 2 times a third is 2/3. 5 times a third is 5/3. We're getting rid of these parentheses. X to the 3rd to the 1/4 is x to the 3/4. Y to the 4th to the 1/4 is y to the 4/4, which is just 1. And then common bases, we have to do subtraction. So 2/3 minus 3/4. Since we're justifying, you might as well show that that's what you're doing. And y to the 5/3 minus 1. And then you can use your calculator, because no one really needs to waste time getting a common denominator. That's not really the point of the problem. So 2/3 minus 3/4 will give you a crazy number. But math fraction will take care of that for you, negative 1/12. So x to the negative 1/12. And y to the 5/3 minus 1, that changes into a fraction, math frac, 2/3. And justify just kind of shows the progression, so we've justified it. There's no need for an explanation. That work is your justification. If it said explain, we would need to maybe write a quick sentence. Let's see if this one can happen quickly. So the zeros of a quartic polynomial, 4th degree, is what that word means. You've got quadratic, cubic, quartic. The zeros are 2, negative 2, 4, and negative 4. From those zeros, we want to construct a possible sketch. So there's nothing that indicates end behavior. It's not like it's saying it's a negative 4th degree, which would have to open down, or a positive 4th degree. We pretty much can do anything. Half of you could do this. The point is, what you can't do is you can't cross at any other place but these 4 locations. And you also can't make any of these a double root. If this is a quartic, and you've got 1, 2, 3, 4 separate roots, they all have to be single roots. So there's no bouncing off of. You just have to cut through, turn around wherever you want, cut through, turn around wherever you want, cut and cut. You cannot bounce. This would technically be a positive quartic because it's opening up, and someone else could do a negative quartic. And that would open down, because even ones have like that bowl-shaped behavior. But this is an option, that's an option. Just make sure you scale, and the y-axis doesn't really matter. I'm counting by 1, 2, 3, 4, and that's enough to scale. You don't have to go overboard and do everything.